Okay. All right. So this is going to be stream 4, I believe. And again, this is going to be a quick one as well because this is one of those smaller blocks in the transformer architecture. More precisely, if I was to talk about it, yeah. So in the transformer architecture, you've got the encoder and you've got the decoder. All right. We haven't talked about the decoder, but I mean, if you look at it, you'll see that pretty much it's got the same blocks except for this thing called masked multi-head attention. We'll get to that part when we cover the actual code block, which is multi-head attention. But let's look at this. I'm skipping one because we covered input, input embeddings, positional encoding, and then we sort of went on to add in norm uh, because it's much more simpler. And then we'll also cover feed forward before going on to multi-head attention. Multi-head attention is not, it's not rocket science, but it just takes a little more because uh, we are not focused on understanding the blocks. That means, how the paper describes them. That's already there. There's a lot of tutorials, information out there for you. What we're interested in is how do you implement all of these blocks using, by leveraging the Rust ecosystem, specifically the Candle crate. So let's look at that. Feed forward is sort of normal. Um, but to sort of just talk about what feed forward is, it's a fully connected network. The idea is basically when we talk about the feed forward layer, uh, the idea is we're trying to sort of um, figure out, in the when we are done with multi-head attention, as you will see when we go to the next stream, we sort of come up with something called attention scores. We're trying to sort of uh, and somehow find a relationship between different words in a sequence. Here, we're mostly interested in each word. We'd like to effectively go ahead and um, apply an operation to each word in in a sequence independently and in parallel, without considering the other words in the sequence. Um, So it's sort of, at least the paper is very straightforward. You take the input, which is usually from the multi-head attention block, as you can see here. So you've done the input, you've added the positional information, you've given it to this multi-head attention block. Then the multi-head attention block goes ahead and, produces something, which is usually a tensor, again, which is normalized. And that normalized tensor passed into the feed-forward block. The feed-forward block is basically a combination of two linear layers and one activation function in between. I believe, according to the paper, the activation function is basically a ReLU. Okay, it's a rectified linear unit. Um, so ideally, the feed-forward block is quite simple. You apply these two linear layers. Uh, every linear layer is nothing but a weight plus a bias vector. Uh, and then when you apply that, you get, a new tensor. Now you apply the activation function to it, and then you go ahead and apply the second linear layer, producing the final output. The purpose of the feed-forward block is to sort of model, as it said, is to allow the model to process the information at each position in the sequence independently, uh, by applying those series of transformations. So it's, you know, I'm still a little, um, not so convinced about why you need this, but I understand that, at least the normalization layer makes sense because you want to normalize your input. You don't want, to have output that is really large, etc. So it's easier for processing. My understanding is mostly about this layer being there so that you can do things in parallel. Um, but why do you want to do those things in parallel? Why do you need this? Is still a question mark for me, to be honest. But anyway, Since it's in the paper and been looking at different implementations, specifically Umar Jamil's implementation, let's take a look at that. So in Rust, how do you do this? Let me just close this. So feed-forward layer in Rust, the way we've implemented it. So if I was to show you the full project, we've got the embeddings part, we've got feed-forward, normalization, multi-head attention is implemented, but I will be talking about that in the next stream. Let's look at feed-forward. So just jump into feed-forward. You see that, I went ahead and did the same thing, exactly what the paper wanted. You've got linear layer 1, linear layer 2, and then there's a dropout. The dropout is, in this case, pretty much the activation function that we want, which is, in this case, a value. All right. Anyway, the way we've implemented this is we're using, again, so if you go look at the documentation that I've written over here, you can create a feed-forward block with the method that's implemented here. But we're using what's called a var map, or a map for variables, which will allow us to initialize tensors. All we need to do is provide it a small config, and you'll be able to, basically produce the result is going to be those two linear layers that you want. You don't have to write it this way because this is very specific. You're instantiating a var map. Okay, by the way, what is a var map? It's just a hash map. All right. So this is a hash map of a string and a var. A var is nothing but a mutable or a tensor that can be mutated in Candle. So in Candle, technically the implementation assumes all tensors are actually immutable, but there's an exception over here. You could use this thing called a var. It's just a wrapper around the standard tensor implementation, where the contents of the tensor can be modified. In general, tensors can't be, according to this implementation. All right. And the hash map, yeah, you should probably know this. It's a standard type from the standard library. So we're saying, you've got name, it's a string, or the app. So that's what a var map is. Obviously, we're going to be working on this from multiple threads. That's why you've got it wrapped in a mutex, which is wrapped in a arc. The arc is to ensure that you could simply do cheap clones and stuff, but yet have multiple ownership. So that's a different concept. That's mostly to do with Rust. But anyway, that's what a var map is. So the reason I sort of went into that level of detail is because you see, I'm actually creating two different var maps. You don't need to do this technically, but you wouldn't want to do that. If you have a hash map, you'd probably want to insert two different key value pairs into the hash map. So why would you want to do this? And it's just to keep this simple. Obviously, there's also a bit of ownership issue that I was facing. So just to avoid that and keep this simple, you can do this. But there is another way to do this, which I probably will talk about as we evolve the model a little more. But yeah, so I'm going to use these two var maps to hold my linear layers. Or in other words, use them to build my linear layers. All right. The reason I have these var maps is because I want to build variables using the var map, and you've got the variable builder type that allows you to build variables, which is nothing but the simple storage for variables. But anyway, so you've got that, and then you've got the dropout. So you've created a new instance. You're great. The paper already says this, and I've put this over here. According to the paper, the two linear layers. Actually, let me just do this. Yeah, this is better. So according to the paper, the two linear layers have the following weights and biases. So the first one is, these dimensions, and B is 512. The second is the weight matrix is these dimensions, and the bias vector is about 2048. So that's great. Now that you've done this, you want to actually go ahead and apply this transformation. So what happens when you do the transformation? If you were to go back to the previous streams, you saw that we do a lot of things, and finally we end up with this uh, shape of our tensor, which is you've got a batch of sequences. Um, the sequences in this case we're taking is, let's assume it's 6 or 8 or whatever it is. According to the paper, it's a sequence length of 6 or a context length of 6. And the dimensions for the model are 512. That means each word is represented by 512 different floats, right? So ideally what would happen is you would, this operation, so you'd first apply the linear layer 1 to the input tensor, then you'd apply the ReLU, and then you'd apply layer, right? So what you apply uh, something that's mentioned in the paper. So that's great. And then you get, so basically you go through this particular sequence. You go from batch sequence D model to batch sequence DFF, which is 2048, and then batch sequence length D model. You could probably, you know what, we could actually verify that everything works. And this is not, an actual, we're not testing this with real input just to see that the whole thing works. I could probably just run this here. All right. Yep. So everything does work. So you got your linear layer 1, linear layer 2, and yeah, so that should be fairly decent. That's all. This is the bias vector for linear layer 2, I think. Okay, so in a very simple implementation, this works. I haven't called forward on it yet. I'm just testing the new part so that, just to see that it works properly. But that's the implementation of it. There's not a lot over here. So you go ahead and provide, uh, you build your linear layers, you build what if you provide a dropout, great, you can go ahead and include that. Or if you don't want to do that, that's fine. But effectively, when you do apply the feed forward layer, this is what happens. So the first layer, linear layer is applied, and then you have the activation function, which is a ReLU, and then whatever the output of that is again passed into linear layer 2. But for that, we also do a dropout so that so dropout is basically randomly zeroing out weights in your tensor so that you can avoid things like overfitting and improve the generalization of your the model's capability to generalize. So we'll get to that. That's important, but we will get to it later. But yeah, that's about it. That's the feed forward layer block, and it should be rather simple. Then I'll also talk about one more thing before we go. The next time when we do the stream, because I do have quite a few other things, but the next time when we do get to this, we're going to be talking about multi-head attention block, which is the most important piece. So let me see if I can find out, yeah, where in the paper this is. Yes. So we will be talking about obviously self-attention, and then we'll also talk about multi-head attention, which is this part. It's not, it's not crazy or something. The most important thing is this formula, and you will see that this formula is actually pretty simple. Okay. All right. We'll talk about this. So this is where you're going to be applying what is called attention. You're going to be doing what's called self-attention, which allows the model to relate words with each other. And when you actually read this and see this, you'll be like, "Ah, that's it. That's it." But it's interesting. Simplicity is generally so powerful. Yeah, we'll get to this part in the next screen. All right, so that's about it. And yeah, thank you if you're watching. That is.